Hello friends, welcome to Bindu Dhadwal chemistry lessons. The topic for today is determination of nature of charge of soul particles. The electrical properties of colloidal solutions are related with two phenomena, electrophoresis and electro osmosis. Both these processes can be used to determine charge of a colloid. Electrophoresis, the phenomena of movement of colloidal particles under an applied electric field, is called electrophoresis. So in electrophoresis, if we add a colloidal solution and this is a U-shaped tube, and we have put platinum electrodes, dipped platinum electrodes in the colloidal solution, and on applying potential, before applying potential, this is the condition, both the arms have same intensity of color of the colloidal soul, arsenic sulfide. But after electrophoresis, after you have applied potential, the negatively charged soul particles get accumulated towards the positively charged electrode. So this tells us that the charge on the colloidal particles is negative because opposite attract. Similarly, if we put ferric hydroxide soul in the same apparatus, it moves towards negative electrode, indicating that it's positively charged. If the movement of colloidal particles is hindered or restricted, in that case the medium particles move in opposite direction, and then the phenomena is called electro osmosis. So electro osmosis is the phenomena of movement of molecules of the dispersion medium under the influence of electric field, whereas colloidal particles are not allowed to move. This is the apparatus. Here the colloidal, the chamber marked A is having the colloidal soul, which has been closed on both sides with semi-permeable membranes, so colloidal particles cannot move through these membranes. And we have this these electrodes which are put in the chambers B and C, which is otherwise filled with water. On applying potential across the electrodes, the level is observed to fall on one side and rise on the other side. So water level falls on this side and rises on the other side because the soul particles are negatively charged and the medium is positively charged. So water molecules will move towards the oppositely charged negative electrode. The medium will move towards negatively charged electrode through the semi-permeable membrane. So medium particles are moving towards oppositely charged electrode, indicating that the soul is made up of negatively charged particles, and this phenomena is called electro osmosis. Coagulation of colloidal solutions. In presence of large excess of electrolyte, the charge on the particles of dispersed phase is neutralized, and as a result they come closer, grow in size, and ultimately form precipitates. A colloidal solution, it is basically stable because the colloidal particles have same charges and they repel each other and remain in solution form and do not settle down. If electrolyte is excess, this excess negative charge on the colloidal particle will be neutralized and the particles will come together and coagulate. So the phenomena of precipitation of a colloidal solution by addition of excess of an electrolyte is called coagulation or flocculation. So according to Hardy-Schulze rule, the ions carrying the charge opposite to that of the soul particles are effective in causing coagulation of the soul. And coagulating power of electrolyte is directly proportional to the fourth power of the valency of the active ions, that is the ions causing coagulation. Greater the valency of oppositely charged ion of electrolyte being added, the faster is coagulation. For example, to coagulate negative Sol of arsenous sulfide, coagulating power will decrease in the order. Positively charged ions having greater valency will coagulate more. So aluminium ions will have more coagulating power than magnesium than sodium. Similarly, to coagulate a positive Sol of ferric hydroxide, coagulating power of negatively charged particles is hexacyanoferrate 2 is more than phosphate, is more than sulfate, is more than chloride. It has FeCN6 has 4 negative charges, so this will coagulate to greater extent. Coagulation value. The minimum concentration of an electrolyte in millimoles, which is required to cause the coagulation or flocculation of 1 liter of Sol, is known as coagulation value or flocculation value. It is expressed as millimoles per liter. And smaller is the coagulation value of an electrolyte, greater is its coagulation or flocculating power. So coagulating power is inversely proportional to coagulation value. So relative coagulating powers can be compared as, to find out the coagulating power of electrolyte 1 with respect to coagulating power of electrolyte 2, you divide coagulating value of electrolyte 2 with coagulating value of electrolyte 1, as they are inversely proportional. For example, to compare between aluminium chloride and NaCl for coagulation of negatively charged Sol arsenous sulfide, we divide coagulating value of NaCl with coagulating value of AlCl3. So you get the coagulating power ratio 51 upon 0.093 will be 548. That means that aluminium chloride has 548 times more coagulating power than NaCl. We took the values from the table. NaCl has flocculating value 51, AlCl3 has 0.093. So next is few other methods of coagulations. First is by mutual precipitation. When two oppositely charged sols are mixed in equimolar proportions, they mutually neutralize their charge and both get coagulated. For example, if positively charged ferric hydroxide is neutralized with the negatively charged arsenic sulfide, both get coagulated. Second is by electrophoresis. We have seen in electrophoresis that particles of dispersed phase move towards the oppositely charged electrode. If the process is carried out for a long time, then ultimately the particles will touch the electrode and get neutralized and coagulated. Then by persistent dialysis, the stability of colloidal sol is due to electrolytes. And if electrolyte is completely removed by repeated dialysis, then the particles will get coagulated. And by heating or cooling. In certain cases, the sol gets coagulated on heating or cooling. For example, butter gets coagulated on heating and milk gets coagulated on cooling. Coagulation of lyophilic sols. Lyophilic sols are more stable than lyophobic sols. The stability of lyophilic sols is due to two factors, charged and solvation of colloidal particles. If the particles are charged, then they will not get coagulated because repulsion occurs, and solvation also prevents coagulation. But when the two factors are removed, a lyophilic sol can be coagulated. We can do this by adding electrolyte or adding a suitable solvent. For example, alcohol or acetone is added to hydrophilic sols. It results in dehydration of dispersed phase particles. Under this condition, a small quantity of electrolyte can cause coagulation. Protection of colloids. When a lyophilic sol is added to lyophobic sol, the lyophilic particles form a layer around the lyophobic particles and thus protect them from electrolytes and coagulation. For example, if a small amount of gelatin is added to gold sol, it is not readily precipitated by the addition of sodium chloride. So, the process of protecting the lyophobic colloidal solutions from precipitation by the electrolytes due to previous addition of some lyophilic colloid is called protection. The colloid which is added to prevent coagulation of colloidal sol is called protecting colloid. The protecting power of different protective colloids is expressed in terms of a term gold number. This term was given by Zsigmondy. He introduced the term gold number to describe the protecting power of different colloids. This is defined as the minimum amount of protective colloid in milligrams required to just prevent the coagulation of a 10 milliliter of a given gold sol when 1 milliliter of 10% solution of sodium chloride is added to it. To understand the definition, let's view it diagrammatically. So this is 10 milliliter of gold sol. If we add 1 milliliter of 10% NaCl to it, it gets coagulated. Now to prevent it from coagulation, we will add collective colloid prior to addition of NaCl. The amount of protective colloid that is added to prevent coagulation, so that no coagulation occurs, is called gold number. So when it was not added, coagulation occurs. When it is added, then even addition of this much of NaCl will not cause coagulation. So the coagulation of gold sol is indicated by change of color from red to blue. In case coagulation occurs, then the color will change to blue. Gold number of some protective colloids is gelatin 0.05 to 0.001, casein 0.01 to 0.02, hemoglobin 0.03 to 0.07, egg albumin 0.1 to 0.2, then gum arabic from 0.15 to 0.25, starch 20 to 25 milligrams, and dextrin 6 to 20. Smaller the value of gold number, greater will be the protecting power of protective colloid, and reciprocal of gold number is a measure of protecting power of the colloidal solution.